Little break and some apple eating, so please.
Okay, yes. Okay, hi, so yes, this is a joint work with Zachary Chase on deterministic apple tasting. So what is apple tasting? Apple tasting is a very slight modification of the standard online learning setting. Let's go over it for a minute. So we have a repeated game between a learner and an adversary. We have a domain of instances, the binary label set, and a concept class of functions from the domain to the binary label set. And in every round, the adversary chooses an example, a labeled example, but it sends only the instance to the learner, and then the learner predicts whether it's 0 or 1, and it suffers loss if it makes a mistake, the 0-1 loss. And this is the modified part. If and only if the prediction is 1, it gets the true label from the adversary, otherwise it gets nothing. Okay, so this is also called apple tasting feedback. So what we're interested in is, as usual, the minimax optimal mistake bound, which is just the expected number of mistakes. And we denote it with M star of HTK for a randomized learner and M star D for a deterministic learner, where K is the number of mistakes that the best hypothesis in class makes. So when K is 0, we are just in the realizable case. Okay, so this is the setting. Now, why would we care about it? So apple tasting is supposed to simulate scenarios where we want to separate the instances into two types, usually good instances and bad instances, where one of the types is, for some reason, gets disappeared after the prediction, and we can't really verify the outcome. So there are many such scenarios we can think of, and one example is just literally apple tasting. So think you want to sell apples, and you want to only send the good apples to the market. So once you decide an apple is good, and you send it to the market, you can't taste it and really verify that it's good. But the bad apples that you keep for yourself, you can taste and make sure that they're actually bad to improve your next predictions. Okay, so if I convinced you that apple tasting is important or interesting, so we can now ask, but why deterministic apple tasting? Because we have perfectly fine randomized apple tasting learners like Feinbold et al. From 2000 and Rahman et al. From COLT last year. So why would we care about deterministic such learners? So actually there are many reasons. First of all, for example, so deterministic bounds hold with probability 1. We have complete certainty. It's not just in expectation. They hold against an adaptive adversary because there's no point in being adaptive when the learner is deterministic. There's just nothing to There's nothing to adapt to. And we don't have to worry that our randomness generation mechanism might get exposed just because we don't have such a mechanism. And at least in my opinion, maybe most importantly, is that deterministic learners are usually fundamental and natural in the sense that they use some core structure of the problem. And famous examples are SOA and weighted majority. Okay, now if I've convinced you that this is all interesting, then we can talk about the results. Okay, so we know that the optimal randomized mistake bound is at most something like order of square root Littlestone T from 2000. Littlestone of the class, of course. And in COLT last year, Rahman et al. Asked if we can get a vanishing mistake bound with respect to T, also using a deterministic learner. So we show the following more general positive result, that the deterministic mistake bound is at most order of square root T times K plus Littlestone log T. And of course, this gives as a special case a positive answer for the realizable case. And we also give a lower bound showing that this upper bound is actually exactly tight up to constant factors for some classes. And of course, this gives also in a special case a lower bound for the realizable case. And interestingly, last year in the COLT paper, Rahman et al. Gave a randomized upper bound of K plus order of square root Littlestone T log T. So I want you to note that there are significant gaps between the randomized and deterministic learners. So even in the realizable case, we have this square root log T difference. And in the non-realizable case, it is much more significant. We have a deterministic lower bound of square root TK, and a randomized upper bound of only K plus square root T as two different summands, which can be really large for some specific K values, for a lot of K values. I just want to know that this is actually a known phenomenon in partial feedback settings, this gap between randomized and deterministic mistake bound. For example, we have a paper last year showing that this happens also in bandit feedback setting. Okay, now to talk briefly about the technique, I want to state a much more simplified setting of realizable experts to demonstrate a bit the techniques. So forget about function classes, forget about instances. We just have n entities called experts, and those experts freely making 0 or 1 predictions adversarially in each round. And we even have a perfect expert that completely realizes the true labels. So we're in the realizable setting. And we can, in this simplified setting, ask for the randomized and deterministic optimal mistake bounds. So what are the mistake bounds we have? So from 2000, we have this tight mistake bound of square root t log n over roughly square root log t. And in this work, we show a tight mistake bound of square root t log n. So there's, again, this gap between randomized and deterministic. And I want to talk briefly about the technique of the deterministic upper bound. So to do that, let rounds of I be the number of rounds where expert I predicts 1, of course, as long as it's still in the game, as it didn't get eliminated by being inconsistent with the feedback. So let's consider 2 very extreme and easy adversarial strategies, but we start with those simple strategies. So in the first strategy, we have just a single expert predicting 1 in every round. So in this case, if you think about it for 2 minutes, you'll see that a good strategy for the learner is to predict 1 once the round's value of some expert reaches square root of t. And if you think about it for another minute, you'll see that this guarantees at most square root t mistakes for this specific easy strategy. Now, also note that for this strategy, the adversary wastes a lot of rounds, like square root t many rounds, on every learner's mistake. So this is one extreme. So if this is one extreme where a single expert predicts 1, the other extreme, the other possible adversarial strategy, which is extreme, is that most of the experts predict 1. Let's say even more than a half of the experts predict round in every round. So this is even more obvious, even that a good strategy here is just to predict 1 every time and eliminate half of the expert every time. And then this guarantees at most log n many mistakes. Okay, and in this case, the adversary just spends 1 round on every mistake of the learner, but it wastes a lot of experts. So in the first extreme, it wastes a lot of rounds, and in the second extreme, it wastes a lot of experts. And we can handle both of them pretty good. So the challenge lies in the fact that it's not obligated to use, of course, one of the strategies, can do a lot of interesting and hard stuff in the middle. So how can we handle this? We just interpolate pretty much between the easy cases and predict 1 when a weighted sum of the experts predicting 1 is large, where the weight is a function of the number of rounds wasted on this expert. So technically, we implement this by using exponential weight. So the weight of I is exponential in the rounds number. And if we do a technical analysis, we have a mistake bound of something like log n over eta plus t eta for every eta and for every adversarial strategy. And if we choose eta correctly, we get the square root t log n mistake bound. And now I want to conclude with an open question. So let me quote like a few sentences from the previous slide. So we said we use an exponential weights forecaster, and we had this log n over eta plus t eta, and we choose eta and get this square root t log n mistake bound. So this probably sounds familiar to some of the people in this room. And indeed, this is a screenshot from the famous prediction learning in games. This is one of the first results in this book, given a regret bound for the most basic full information expert setting. And here we also have the exponentially weighted forecaster, and we get this exact same expression with this any eta. And this raises a natural question of whether this randomized, non-realizable, full information, standard, well-known expert setting is in some sense related or even somehow equivalent to this deterministic, realizable, apple-tasting expert setting. And that's all I have. Thanks.
Thank you. Do we have questions?
Like that's kind of related to the last question that you were asking. So I was wondering, like this new kind of feedback. If you
Should I get?
yeah, this thing. So I was wondering if you can generalize this to a much more general settings like linear bandits and all, and if there's an analog version of any question in that space.
Okay, I don't know if there's an analog in linear bandits, but
Yeah.
I think trying to generalize this is an excellent question. Like maybe there's a more general setting somehow integrate both in a way that gives you like a framework to analyze all kinds of those settings. That would be very nice. Thanks.